Hey guys, welcome back. This is day 14 of rotation dynamics, and I forgot to tell you about this thing. About the simulations about in this website ophysics.com. So we remember this problem where you conserve the angular momentum. You can change the size of the disk. You can change the man's position. If I put him at the extreme, you can clearly see that he is going with a very low angular velocity. The whole disk is going with a very low angular velocity, and if I pull him close, you can clearly see the disk has gained some angular velocity, right? So this is basic conservation of angular momentum. It is there in the website ophysics.com. Go ahead and check it. The next thing that I wanted to check is the result of is an interesting thing. Remember the problem where we've talked about putting a force on a body at the center of mass or at some random point, at the center of mass or at the some random point. In I clearly told you in both the cases, the center of mass accelerates with F by m only. No matter, even if I put the force at the center of mass or if I put the force at the edge. In the edge case, it actually linearly accelerates and there is some angular acceleration also for sure. There is some angular acceleration and there is linear acceleration also. But I clearly told you, I remember telling you that in both the cases, when I put it at the center of mass, when I put it at some random point, the center of mass accelerates with the same acceleration a by m. This right here is a proof of that, except we don't have the force, we have the impulse. You see that the gun in the first case is clearly aiming at the center. In the second case, I can aim it anywhere. But no matter where I aim it, you clearly observe that the center of mass clearly goes with the same velocity. Get ready, I'm firing. You see that? In the second case, it's just the body is angularly moving, that's all. Other than that, both the bodies clearly have the same linear velocities. Both the bodies have the same linear velocity. It's just the other body will have some angular velocity. So remember the point, it doesn't really matter where you apply the force. As long as linear is concerned, the acceleration or the velocity is gained is totally same. When the position is different, like when you apply a force here or here, it simply changes the direction of angular velocity or the amount of angular velocity. Let me put it a little nearer to center of mass and fire it. You see the angular velocity has decreased, that's all. But still the center of mass is going with the same angular velocity. So which is an interesting thing. I'm going to put it exactly at the center of mass itself. Let's check what happens. Obviously, oh, not exactly at the center of mass. I missed it by a small amount. So you can clearly see that there is a little angular velocity. I don't think I can actually aim it exactly at the point. Can I aim it? Oh, it's not the gun that I should aim. I should aim the blue dot, I guess. Let's check that. I missed it again. It's fine. If I put it here on the other side, you can clearly see it is rotating in the other direction. That's all. But important point is the center of masses are clearly going with the same angular velocity. So I just wanted to show you that. Uh, this is a very important thing. I wanted to discuss about this. A particle colliding with a rod, a particle colliding with a rod. Like, what is the one principle that we need to follow when this particle is colliding with the rod and sticking to it or not sticking to it? Can somebody tell me what is the one principle that we need to follow? Yeah, I'll run the simulation for you. This is what's happening. The particle came in, stick to the rod, and they're both swinging. Let us bring down the mass of the rod a little so that you get more swing. Yeah, you see that? Obviously, there is more swing. Show the line of sight and center of mass and maximum angle and all. Yeah, I'm going to bring the mass of the rod much further. It is clearly rotating. Can somebody? It is hanged. There is too much of FPS. I guess it stopped. Yeah, the screen is paused. I get it. Whenever there is too much of frames per second, I think it is not able to handle it. Too much of animation, maybe. Yeah. Now you can see. So can somebody tell me what is the one principle that we need to follow? Aniket, you have something?
The conservation of angular momentum.
Beautiful. That's all we need to do is simply conserve the angular momentum in that case. So in physics, like whenever they discuss this as a very big topic, but I don't really like to do this. Okay, they take this, they take the particle is coming, and once it is once it hits the rod, and let us just imagine the in the case where it sticks, so they're both going with the angular velocity. I'm considering the whole system's angular momentum about this point, and this whole thing is a system, like the both the ball and the rod as a single system. Can we conserve the angular momentum? Of course, like there is no external force on this thing, so obviously during this collision we can conserve the angular momentum. Guys, please remember that gravity is there. We are only conserving the angular momentum between these two moments, just before the collision and just after the collision. We're not conserving the angular momentum when it reached there. You're clearly getting that. To get there, we're simply using the work per energy theorem only. We will do a question which is related to this today. Okay, we're not doing it all the way. We are only doing it just before the collision, just after the collision. Aditya is asking what if it is an elastic collision and all. We will discuss all the problems, but this is the basic problem that we can discuss. That's why I started with it. Okay, please observe the point that we are just before collision and just after collision we are conserving the angular momentum. Good that Aniket mentioned that. So let us write that. Let us take the big rod's mass as m, length as l. It small rods m came in with a velocity v. What is the initial angular momentum of the system? For this, about this red point, mv into perpendicular distance l, mv into perpendicular distance l, plus the rod has no angular momentum initially, so there is no angular momentum. Final angular momentum, like I will write the moment of inertia of both ml square by 3, plus for the particle it is basically ml square into omega. So I simply equate these two and I find the angular velocity as, this is not equal, okay, this is equal. Angular velocity is basically mvl by ml square by 3 plus ml square. Now, once you find the angular velocity, you can use the conservation of energy. We've just done that in the last, like a problem in yesterday itself. Like it has some angular velocity omega. How high can it go? To what angle can it actually go with the angular velocity? We can definitely do that. Shall I do a problem? Like, shall we discuss a problem which is entirely like we can actually practice it? And shall we check that in the units? I don't think we can put our masses there. That will be too much of calculation for you to do, so we don't do that. Let's not go into numericals. Let's just do a simple problem that we can do. Okay, uh, a rod hinged clearly of mass 5m, length l. Now get ready, a particle with a velocity v hits it at 3l by 4 and sticks to it. So right after the collision, what is the angular velocity? That is the first question. Right after the collision, what is the angular velocity that it gained? And the next question is, to what angle do they actually raise? If you can find the angle, that would be great. You can do it. But even if you don't do it, it's totally fine. But find the angular velocity first of all and let me know. Mass of the ball is m. Yeah, I'm sorry. Do it. I'm giving you a minute. Try it and let me know. All you have to do is take the angular momentum, Anybody has any answer?
Sir,
Yeah.
12 by 107L.
107. Why do you have 107?
It came like that, sir.
Acha, because of 3L by 4.
Yes, sir.
Yeah, maybe. Yeah, there is a chance that you might get it. So m into v into 3L by 4 is initial equals to, after that, 5m L square by 3, that is for the rod, plus m into 3L by 4 whole square into omega. Is this the equation that you got? People are getting different answers there. Harshavardhan says a different answer, and I don't know. I don't know the answer, guys. But if you get this equation, you might have gone wrong in the calculation. That's all. Okay. So please check that. Please check that.
That
And
equation only, sir.
yeah, yeah. Once you get this equation, it's easy to do it. Now, if only you want to find the angle, what do? You write the kinetic energy here, half I omega square when it is at the point like this. Now when it is raised, so you make sure the amount of height raised by the particle, you make sure the amount of height raised by the center of mass also. You write the potential energies of both, equate it to this, you write the potential energy, and that is how you can find the angle. Okay, I'm not sure with the calculations, guys. Here you guys go ahead and do the calculations now. Let us move on to a bigger problem now. A bigger problem is, Sharad, which part did you not understand? Please raise your hand.
So for this one, we have to find the combined center of mass of the
Yeah,
particle
you
and.
can do that. You can simply take the combined center of mass, height raised, and all. You can do it.
Sir,
Sharad,
once you can show it, it's confusing.
fine. I'll do it. I'll do it, guys.
Same dot, sir. How are we supposed to find the angle?
Yeah, 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 yeah. Let me do it. So this is the center of 5m. So 5m is present here. This is the center of m. The center of mass will be somewhere around here. This is the center of mass. Whose distance we can calculate it as, how do we calculate this distance? Let's do some math. Like, let us take this as horizon, and let's write distances. M into 3L by 4 plus 5m into L by 2 by m plus 5m. Everyone knows, remembers how you find the value of YCM, I hope. So once you find the center of mass, you can simply take the whole system, like no matter what it is, the whole system is at a distance, that new distance, the center of mass distance. Let's call this as YCM only. Now when it raised to an angle theta, what is the amount of height it raised? If only it was L, like, do you remember this thing? If only the distance was L and it raised to an angle theta, it was L into 1 minus cos theta. L into 1 minus cos theta. Normally, like when we used to do the problems. Now we found this YCM. We can find this YCM. So that YCM has raised to a distance of YCM into 1 minus cos theta. This is the height raised into mass, total mass, 6mgh. You have 6mgh equals to half I omega square. I guys, do you get it now? From this, can you find the angle which is right here? The angle. Yeah, Niket, get it. Sharath, do you also get this? For people who didn't practice a lot of questions, this might look like Chinese or German, or it could be Hebrew. I don't know, but I blame you people whoever is totally practicing every day. They're totally getting all the problems. So if you're not getting these problems, you probably didn't follow all the classes till now. So I'm also observing one more point, that not a lot of people are clearly following each and every class. If you just come back, blame it on me, no, I don't accept it. Because a lot of people, I clearly see that a lot of people are not watching the classes again, and you're just ignoring it. If you ignore that, I don't really have anything to say in that case. Okay, you will just face the consequences. Okay, Yeah, let me move on to the next problem, which is asked by somebody asked, I don't remember. Let us just imagine the collision is elastic now. The same problem, capital M, small m, the particle came in with a velocity v, the collided, the length is L, but the collision was elastic or perfect, not even perfectly elastic or elastic, somewhere in between there. They even give you the value of E. Okay, don't go that far. These are we are already going really far. Okay, guys. Wait a second. For BPC students, you don't really need to go this far. Okay, you are already we've already crossed your line. We've already crossed way over your line. So you don't really need this kind of collision problems in rotational dynamics. This is way too much for you. The kind of problems that you might face is basically moment of inertia, angular momentums, angular momentum conservations, and that's all. So, yeah, let me do the problem. Let us just imagine this is a collision, which is some elastic collision. Let's just deal with the elastic collision first. Let's just say the ball came in, collided. Right after the collision, this gained some angular velocity and the body has returned with the velocity v1. So this whole thing happened. It came in, collided, and returned with a angular linear velocity v1. So what happened? This whole thing is a system again. Since this is a hinge, I am taking the angular momentum about the hinge again. I'm taking the angular momentum about the hinge again, just before the collision and just after the collision. Let us look at the whole problem. Just before the collision, mv into perpendicular distance L, mv into perpendicular distance L plus angular momentum of the rod is 0. So that is the initial momentum, angular momentum. Now final angular momentum, when I write about the same point, I'm going to write for the particle as minus mv1L. I hope you get why I write minus v1, because it clearly changed the direction of angular momentum. Previously, the angular momentum's direction for the particle is in this direction. Now it is in this direction. For the particle I'm talking about. For the rod, it is in the same direction. So for the rod, it is plus I omega only, plus ml square by 3 into omega. So you can happily equate this whole this equation with this equation, but we are not done yet. We are not done yet. We have a very important thing to care about. They don't give you the v1 velocity also. They directly mentioned E equals to 1, or it's a perfectly elastic collision. Since it is a perfectly elastic collision, I hope you guys understood this bit. If you didn't understand this bit, like how I write the angular momentum, please raise your hand, because we need to go one more step ahead in this problem. If it is an elastic collision, this is not a sticking question, this is an elastic collision. So if you didn't understand this bit, please raise your hand. Okay, I think you people get this part. Now, they don't even give you the velocity v1. We need to write another specific equation, which is I'm writing L omega as the velocity of this point. The reason is like R omega. It is rotating with omega, so this point is clearly going with L omega. The velocities that we have right here, right before the collision and right after the collision, before collision and after the collision, the velocity that we have simply give us what? The velocity of approach and velocity of separation. E equals to 1. If you remember, E equals to 1, which is nothing but V2 minus V1 by U1 minus U2. Velocity of separation minus velocity of approach. I'm going to write L omega minus of minus V, for this is velocity of separation. L omega minus of minus V. Velocity of approach is basically V minus 0, because this particle has 0 velocity. So E equals to 1. So 1 equals to L omega plus V equals to V. Wait a second. We are getting a value which is wrong. Plus V. So V0, L omega equals to 0. You're getting omega equals to 0. I don't think it should happen. Did I commit a mistake anywhere? Oh, this is V1. I'm sorry. I'm sorry. I'm sorry. Someone should have mentioned it. This is V1. This is V1. Why you people didn't tell me that? You idiots. No, I'm the idiot trusting you people. So V equals to L omega plus V1. We have this equation. This equation is done. And the angular momentum equation. You use this equation and this equation to solve the entire problem, which is a very big problem. I would definitely agree. But yeah, it is a part of a syllabus. Now, Aniket is again going to ask whether this comes in mains exam. No, it won't. But for advanced level, there is a chance that you might get a question like this. So you need to be careful. Aditya.
Sir, there are some cases like we take the rod is made up of wood, and I'm firing a bullet, sir. Now the bullet will go passing that wood, sir. Then what should I do?
Beautiful, beautiful question. Which is a similar question and like completely similar question. This is a wood. I'm glad you are making questions out of your own brain. That is a good thing. This is what the initial case is. Right after the collision, the rod, it has passed through the wood. So the bullet, the rod has gained some angular velocity, and the bullet has come out of the other side with V1. Aditya, you tell me what's the only difference that it will make when
I
I write
think
that.
V1 should be not in the same direction. Like we need
Exactly.
not
So
take anything
MVL,
negative.
MV1L plus I omega. You get it?
Okay.
I have
Yes, sir. Now,
that rod ml square by 3 omega. You get that?
yes, sir.
Yeah,
Yes,
yeah.
sir.
So this is how you write the angular momentums. Now I'm not going to stop. If your brain feels like fried already, put it under ice. Aniket, what is it?
The pulley slipping one we'll have.
Police, what?
The string slipping over the pulley.
No, 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 no. So it won't slip. It will rotate along with the thing. Okay, don't worry. Why are you so worried about all the things that are about to come?
Just like that, sir.
Rotational mechanics scared you, right?
Yes, sir.
Yeah, a little. But yeah, the worst part is almost over. Like if this part is over, rolling motion is not that difficult. Rolling motion is easy only. Once rotational mechanics is done, there is just all fun part only. I mean, like I love rotational mechanics, but it's way too complicated for a lot of people. Once it is over, we have to go through gravitation, SHM, and all. They're like really lovely topics. You don't really face a lot of issue there. So this is the hardest part. Just go through. Just stay with me and let's go through it. The next problem is there is no hinge, and M is coming with V. Anybody? Any ideas? Raise your hands. M is coming with the velocity V. There is no
The
hinge.
combined translation rotation.
Exactly, combined translation rotation. And
Yes, sir.
what do we need to do here? Like we conserve the
Take
momentum?
that hinge as the center of mass, sir.
Take what?
Take center of mass as hinge.
Okay, that's a very
Like
good
the
idea.
point
How
where
did
the
you
center
how
of
did you
mass
get that
lies.
idea?
From previous translation problem, sir. Like whenever there is no hinge, just imagine the center of mass as the hinge.
So this is there are two things here. One, it can stick. So one, it can be an inelastic collision. One, it can be an inelastic collision. The other, it can be an elastic collision. Right?
Yes, sir.
So guys, remember, I'm going to tell you something here which might look strange to you. Since it is collisions, you can happily conserve the linear momentum for sure. You can conserve the linear momentum. There is no hinge. There is no hinge at all. You can conserve the linear momentum. Sharath, what is it?
Sir, when the ball strikes the rod, sir, the rod will fall, right? So there won't be any hinge action.
Yeah, there won't be any, like, yeah, I'm not talking about a case where there is gravity anymore. Okay, let's just forget about gravity and all.
Isolated in space.
Yeah, isolated in space and the collision is happening. Okay, like I forgot to mention that. Or you can simply consider that the whole collision is happening on a horizontal space. If the rod is sitting horizontally, a particle is coming and hitting it. You can consider that also, right?
Yes,
The
sir.
total momentum can be conserved.
What?
Total momentum, linear and angular.
Yes, that's where I'm. Of course, total linear momentum and angular momentum can be conserved, but the linear momentum is conserved here. The angular momentum is conserved here. But the angular momentum about which point? About the center of mass of the rod can be conserved. About the center of mass of the rod. But if it is inelastic, guys, we are seriously entering. Like this is a topic that I used to teach those students in China branch. You know those people 1, 1, 2, 2 ranks. I mean, I didn't teach. I used to clear some doubts to these people. Like someone else used to teach him. This is a very difficult case. This is a very difficult case that we're talking about. In this case, linear momentum is conserved for sure. Angular momentum is also conserved, but angular momentum is only conserved about the center of mass of system. Center of mass of system. Please remember this point. It is conserved about the center of mass of the system. Akshat Pambi, I can't unmute you. I don't know why. There is no mic at all.
So why only about center of mass of system?
Like you tell me. We've discussed this thing today already.
Yes, sir.
Yeah. We
No,
are
sir, but
taking
we can
about
still conserve with pseudo.
we are taking about the center of mass of the system because there is some pseudo forces or pseudo impulses. So it is safe to take about this point. Okay.
Okay.
Now this the chance of you getting a problem where the rod is not hinged is like 0.0000001%, but not 0. Okay, because this problem is way too difficult when you have a rod not hinged and it is being hit by a particle, which is a very, very difficult case. So the chances that you get a problem like this is very, very slim. But still I have to teach you, so I'm teaching you. So whenever you face a problem like this, bring it to me and we will discuss for sure. Bring it to me, we will discuss for sure. This is not over. I'm just giving you the glimpse of the problem. But this is not clearly over. We will definitely discuss this thing. All right. So they take all these kind of 4 cases, 1, 2, 3 and 4. Like before hinged, there are 2 cases in hinged, there are 2 cases in non-hinged. So they take all the 4 cases as 4 types of collisions. 4 types of collisions in rotational mechanics. They consider it as a really important, like really big topic. Okay, like they teach it separately. I didn't want to confuse you people, so that's why I took it slowly. So I hope I made sense. Even if I didn't, I suggest you to watch this video again and again. You'll probably get there. But if you get more doubts about it, I'll definitely try to discuss them. All right. So I'm moving on from the one of the worst, or one of the most complex ideas that we're ever going to learn. That part is over. From this point onwards, everything gets easy. Okay. From this point on, everything gets easy. So take a deep breath and settle in. There is rolling for sure. I will just introduce the idea to you today, which is an easy topic. It's not really easy. Aditya is asking, what about oblique collisions in the previous problems? Aditya just doesn't want to sleep. Aditya, if the collision is oblique, let us just say if the collision is oblique, like the bullet is coming in this direction, you write the angular momentum, write this as a perpendicular distance. That's all. Aditya, do you get it? All you need to do is perpendicular distance. Take the perpendicular distance and solve it. This guy just find his address and go ahead and kill him. I don't really mind. So yeah, let's take a breath and let's settle with easy questions. Aniket, what?
Sir, for that oblique collision, the rod will not go in some 2D way.
I don't know. Let's check. We have that simulation. So reset. Let's have the
Without hinge,
particle.
sir.
Let's have the particle collide in this direction. Still going that like that only.
No, sir, without the hinge.
Yeah, it'll go in a 2D motion for sure. Why do you want to solve a problem like that? Yeah, even in that case, it depends whether there is friction in between both the bodies. Have you ever done a problem of collisions with friction involved, Aniket? Aniket, have you ever done a problem with friction involved?
No, sir.
Yeah, do you want to do that too? I can give
No,
you
sir.
problems where the friction is involved in a collision also. So rotational mechanics, friction collision. So yeah, let's do it. Why not give it an angular momentum also? So yeah, why not do you solve a problem where Ravichandran Ashwin has given a ball a linear velocity and some angular velocity. So the ball is spinning and linearly going, and when it bounces on the ground it has some coefficient of restitution, and there is friction in between the ball and ground, so there is a friction coefficient. I'll give you the friction coefficient. Find by how much angle the ball is spun from its original path. We'll do that problem.
My head will burst.
Sir,
Yeah, Spamsi, tell me.
sir, if the ball is if the rod is not hinged, it is attached to the spring,
Yeah.
and the particle is hit.
One important, like, let's not discuss those things here, okay? Like, you're bringing springs into the action, so things get really, really complicated there. Okay, it doesn't really get complicated when you have a spring in a collision. Springs don't really affect you immediately in a collision, but after the collision there is more action happening, so we don't want to discuss all these things. Is Aniket still crying? Aniket, you need to find the angle of deviation from its original path since Ravichandran Ashwin is bowling. Yeah, Aditya.
So you gave this problem to Aniket na sir. One thing I wanted to ask sir.
Yeah.
The ball is spinning. So when it rebounds from the ground,
Yeah.
if the friction is more, the ball will spin in the opposite direction, or it will continue to spin
So
in that same direction.
depends on the frictional impulse that you received from the ground. If the ground is like extremely, what do you say, rough, there is a chance that the ball might spin in the opposite direction also, or the ball simply could still spin in the same direction. So it
Just
depends.
slow down.
It depends. It simply
It's
slow down.
a bit
Yeah.
slow then.
Yeah. It's simply like, those bouncy balls, right? Like, we used to throw them, spin them, and throw them forward. It used to bounce, come back,
Yeah.
but when it comes back to us, it actually spins in the opposite direction and goes
It has
back.
this
Like, it
different
kind of
spin.
does this kind of a motion. So in that case, it is actually changing its direction constantly. So no, that is a different case. It depends on the
In mini
material
ball we can
properties.
see this sir.
Yeah, it depends on the material properties. Today's class is way too much for a lot of people, I'm sure. So yeah, I was gonna discuss something. Yeah, a simple problem that we need to discuss. One more idea with rotational kinetic energies. A very simple problem. Like, from this point onwards, trust me, it gets a little easier only, not complications. You release a body here. When the body is vertical, it definitely has some angular velocity, and everyone knows how to find this angular velocity. They ask you, what is the normal force in this situation? What is a normal force in this situation? Can anybody give me any idea? How do you find the normal force? Obviously there is gravity, mg, acting downwards, but along with the mg there is another force, which is what? Anybody? No? Because of this thing there is mr omega square, remember? Pseudo force, I mean the centrifugal force. All you need to do is find omega, put it mr. L, r is nothing but L by 2. You need to talk about the center of mass only. The centrifugal force actually acts on the center of mass only, so ml by 2. So the normal force simply becomes n plus n equals to mg plus ml by 2 omega square. Okay, so this is another idea. Just like, you might face some problems with this idea, you need to solve those, so be careful about that. Yeah, Niket.
It will be minus, right, sir, because it's accelerating towards
But you're writing a
the
centrifugal force. You're writing the centrifugal force. You're in the frame of reference of body. You forgot the circular motion also.
Oh, okay, sir.
Yeah, you're in the frame of reference of body. You write the pseudo force. Okay. So let us talk about. I'll just give you a small glimpse about rolling. Let's talk about toppling first, and then we go to rolling. They're not two different topics. Toppling and rolling are the same things. How do I explain toppling? I don't have any body except the only body that I always find is my phone. My phone is standing like this. Okay. Wow. It almost fell off my face. So I'm applying some force to it. I'm applying some force to it. I need to apply some enough amount of force that it should raise like this and topple. This is simply toppling. So to this, for this to happen, clearly observe there is a point of contact. There is a point of contact about which the body simply rotated. So I'm going to draw the body here from the side view. Half of the people left the class. You apply, let's not apply it at the center. Let's apply it here. Mg is acting here. And this people is a point of rotation. About this point, F is creating a torque in this direction. Mg is creating a torque in this direction. All you need to do is create enough torque with F. All you need to do is create enough torque with F, which balances the torque of Mg. So the body topples. That is what called as toppling. Okay. Now, I'm just giving a glimpse of it. Tomorrow we will discuss the problems on toppling. We don't want to, take a lot of stress today. So this is basically toppling. We will find some forces like what is the amount of force and all. We will do all these kind of problems. But we have, let us say, another body like this. To topple this also about this specific point, you need to apply some force which creates some torque that is balanced by mg. Let us just imagine there are more sides now. There is another body. I'm not even sure if I can draw another body with more sides, like hexagon. I'm not sure if I've drawn the hexagon or not. But even for this body also, the point of contact is there. You clearly need to observe that this point of contact comes closer and closer to this point. And at some point, when you have a round body, the body is basically, yeah, somebody says more, the like if you have more number of sides, you need less amount of force. There comes a point where the body simply topples about the point of contact itself, and that, my friends, is called as rolling. Sharath, what's your doubt?
Sir, in these cases, sir, for the pentagon and the decagon, sir, there's no point of contact, right? There's a plane of contact.
Yeah, there's a plane of contact, but if you apply a force, this will be the point of contact. Like the body will tilt about that point only, right? This whole
Yes.
plane is in contact, but this point, about this point only, the body will rotate. Like I said in my phone, in the case of a phone, this whole side, the plane is actually in contact, but when it is tilted, there is only one point of contact. Do you agree?
Yes, sir.
Yeah, so that is the point of contact that I'm talking about. So this is basically rolling, and we are going to talk about rolling in the next class, which is not tomorrow, because tomorrow is just a problem discussion thing. We'll discuss all the problems tomorrow. Yeah, Aditya is asking again. He's making things really difficult. What if it slides off and all? We will talk about all these things. There needs to be some friction for the body to get into rolling and toppling. We will all talk about all these things tomorrow. Let's just take some rest today. Okay, I think all your heads are already heated up a little, so let's just take some break for today. I'm not even going to discuss any more doubts today. I can clearly feel the energy that is there in the class right now. So let's just end it. Let's just end the session. If you have any more doubts, like text me and we will discuss them. So, thanks so much, and bye bye for today.